Hello everyone! In today's webinar, we'll explore how multibody dynamics technologies can be applied to the shipbuilding, offshore, and marine industries using RecurDyn. In this webinar, we'll begin with a brief overview of what multibody dynamics is. Then, we'll discuss how to define fluid behavior to analyze the motion of floating or underwater structures. Finally, we'll explore application examples of multibody dynamics technologies that can be applied to the shipbuilding, offshore, and marine industries. On a vessel floating underwater, there are various types of equipment installed such as anchors and sails, machinery for loading and unloading heavy cargo, and systems that ensure safe and efficient operation. In addition, special purpose ships are often equipped with customized devices designed for their specific missions. When designing such equipment for ships, are there any unique considerations compared to general mechanical systems? One of the key factors to consider is how to ensure that the waves and the motion of the sea do not negatively affect the performance of the onboard machinery. When conducting multibody dynamics simulations, it is possible to include the effect of the incident waves on the vessel and the wave conditions. Then, I will explain how to model the fluid behavior for multibody dynamics. After that, I will discuss the applicable dynamic analysis techniques for ships and offshore structures. Before we look at the technologies applicable to the shipbuilding, offshore, and marine industries, let's start with a brief overview of what multibody dynamics is. Dynamic analysis generally refers to calculating the position, velocity, and acceleration of a body over time under applied forces. As an extension of this concept, multibody dynamics refers to modeling a mechanical system composed of multiple components. By defining joint constraints, prescribed motions, and applied loads, and by considering the force transmission between components, we can calculate the overall behavior of the entire system. RecurDyn is a simulation software that performs the multibody dynamics analysis described earlier. It calculates the position, velocity, acceleration, and applied forces between components in a defined mechanical system and presents the results through animation and plots. RecurDyn provides a comprehensive analysis environment that extends the concept of dynamics analysis beyond the rigid bodies and includes flexible body analysis, fluid analysis for shipbuilding and marine applications, and system control analysis, are seamlessly integrated into one specialized platform. When you look more closely at the applications of multibody dynamics, RecurDyn is widely used in various industries such as automotive and defense, including tracked vehicles. It is also applied to electronic devices like printers, construction equipment such as excavators, and automatic systems, including robots. In addition, it is used in systems that require fluid analysis such as washing machines, as well as the aerospace and precision machinery industries. We would just look at the general concept of multibody dynamics. Now, let's explore how MFBD can be applied in the shipbuilding and marine industries. When it comes to applying multibody dynamics in this field, what do you think is the first thing we need to consider? It's fluid behavior. Let's take a closer look at how fluid behavior is modeled and analyzed in dynamic simulations. Let's consider a material handling and transport equipment such as a chain crane that lifts and moves heavy objects. Even on a vessel floating on the water, we often need to handle and transport heavy cargo using such equipment. So, when you use this kind of equipment on a ship instead of a land, what else do we need to think about? When cargo is moved on a ship, it changes the overall load distribution of the vessel. This, in turn, affects the ship's orientation and position as it floats on the water. Such changes can apply unexpected forces and directions of load to the equipment installed on the ship. Therefore, machinery designed for shipboard use must consider the ship's motion on the water. So, how can you perform a dynamic analysis of these devices while considering the motion of a floating ship? Let's consider a floating solar panel system as an example. The floating structure on the water can move up and down, forward and backward, and side to side, depending on the wave height. It can also rotate, changing its orientation as it moves. From a dynamics perspective, this motion can be defined as 6 degrees of freedom consisting of 3 transitional motions and 3 rotational motions. Let's take a look at the simulation results of a floating solar panel system on the right. In this model, each floating unit was defined with 6 degrees of freedom to analyze how it moves on the water. As you can see, each unit moves it independently, creating relative motion between them. This causes deformation in the connecting components, and the level of stress is visualized in different colors as shown in the animation. A similar approach can also be applied to the ships. In this case, we can measure the ship's orientation and position using motion sensors and use the data as a 6 degrees of freedom motion input for the dynamic analysis. By modeling a ship in this way, we can use dynamic analysis to simulate and evaluate potential issues that may occur in onboard machinery due to the vessel's motion during operation. Just like the floating solar panels example seen earlier, this approach allows us to analyze how floating structures behave on the water and assess the impact on connected or installed components. It is particularly useful for evaluating control systems designed to maintain a stable orientation regardless of the ship's motion. As shown in this example, the 6 degrees of freedom motion can be applied when testing control systems installed on ships, including naval vessels. These systems are designed to maintain a specific orientation or direction even while the ship is in motion. For instance, this method is often used to analyze two-axis stabilization systems that keep onboard equipment steady at a desired angle. How should we perform dynamic analysis when a moving load on the water affects a vessel's orientation and position, as seen with the offshore crane on the left? The video shown here compare physical test results with RecurDyn dynamic simulations, demonstrating how the motion of the floating machinery changes buoyancy in real time. As the load moves across the water, its center of gravity shifts. When the moving object makes contact with the water, and buoyancy is generated. The applied loads also change accordingly. Even when the object shape remains the same, the submerged volume can vary depending on its orientation, resulting in differences in buoyant force. As a result, changes in external forces acting on the entire system appear as changes in the vessel's orientation. The key factors here are the changes of the center of gravity and the variations in submerged volume, which lead to changes in buoyancy. To analyze this effect dynamically, it is essential to accurately calculate the submerged volume based on the geometry below the water surface. Then, we need a dynamic analysis capability that can precisely convert this volume into buoyant force. The videos here show RecurDyn models that calculate the buoyancy based on the submerged geometry of objects with various shapes. Earlier, we looked at how defining the 6DOF motion of a vessel allows us to analyze how onboard machinery is affected by the ship's motion. In contrast, defining buoyancy in this way aims for a different purpose. This modeling approach focuses on analyzing how the motion of machinery installed on a vessel influences the vessel's orientation and position while floating on the water. The example on the left uses RecurDyn's buoyancy calculation feature. This model analyzes how a tank-shaped object moving at a constant speed and direction on the water moves up and down due to buoyancy. In this video, the water surface is shown only to indicate the water level. As you can see, simulation results using buoyancy does not take into account the effects of waves or wave conditions. That is, it does not consider the fluid motion or pressure caused by an object moving on the water. So, what if we need to consider the detailed fluid behavior itself under the same conditions? In this example on the right, a tank is moving through a narrow channel pushing the water aside. Due to the waves, the tank is sometimes submerged and then lifted by buoyancy, oscillating up and down. The tank's body affects the water, and the water in turn affects the tank's motion. To analyze such interactions, we need to simulate both the dynamic behavior of the mechanical system and the fluid behavior that responds to it. On the left, you can see a simulation that analyzes how water flows into the building interior. On the right, the analysis compares an experiment showing sloshing and splashing behavior when a barrier in the middle of a rectangular tank is suddenly removed. Both the simulations were performed using Particleworks, a particle-based CFD software. Particleworks simulates fluid behavior using the motion of countless particles and the interaction between them. Both the examples show fluid behavior within a fixed space. If this method is applied to a moving space or moving geometry, it becomes possible to simulate the interaction between a moving mechanical system and the fluid. RecurDyn offers an integrated analysis environment that allows the two-way co-simulation between multibody dynamics model and fluid model through its special interface with particle-based fluid simulation software, Particleworks. This video shows particle-based fluid simulation results. In addition, the results can be rendered to visualize the free surface motion more realistically. As seen, one of the most essential aspects of dynamic analysis in the marine and offshore field is how to model and analyze floating bodies. To review briefly, there are three key analysis approaches. First, using 6DOF motion to evaluate how the motion of a floating body affects the onboard machinery. Second, including buoyancy behavior to study how the motion of onboard machinery influences the floating body itself. Third, performing two-way co-simulation between fluid and multibody dynamics to capture the interaction between mechanical systems and fluid. These three techniques represent the core dynamic analysis methods required for marine and offshore applications. Before deciding the method, it is essential to have a clear understanding of the system to be analyzed and the purpose of the analysis. Based on that understanding, you can apply the most appropriate modeling approach and analysis technique to achieve meaningful and reliable results. Now, let's take a look at other multibody dynamics technologies that can be applied to the shipbuilding, offshore, and marine industries beyond what we covered so far. I will explain them using some reference images and RecurDyn example models. As briefly mentioned earlier, multibody dynamics is a technology that analyzes the physical behavior of mechanical systems in motion. While this analysis is generally performed under the assumption that mechanical components behave as rigid, non-deforming bodies under applied forces, rigid bodies can be converted into flexible bodies that deform when subjected to external loads. This is called MFBD or multi-flexible body dynamics. RecurDyn provides an easy and fast simulation process through its CAD-based modeling environment and high-fidelity computation capabilities. It allows you to define constraints, forces, and various contact conditions involving both the rigid and flexible bodies quickly and precisely. Now, let's look at how these dynamic analysis technologies can be applied in the shipbuilding, offshore, and marine industries. First, let's take a look at the examples where fluid analysis and dynamic analysis are used independently. This example shows the fluid dynamics results of an oil spill accident from a tanker. Although it is a simple example, it shows how simulation is used to analyze fluid flow within a defined region of the ocean. This example shows where only dynamic analysis was applied. This is a tracked vehicle used for deep-sea mining. Ground settlement is caused by vehicle travel. In turn, it affects the vehicle's running performance. This analysis applies tracked vehicle dynamics together with the techniques that account for ground settlement. Assuming that the effect of the fluid is negligible, the simulation was performed using only multi-body dynamics. Through the two examples presented on this page and the previous one, we've seen how fluid dynamics and multibody dynamics can each be applied independently in the marine and offshore fields. Next, let's take a look at several examples where fluid dynamics and multibody dynamics can be applied in various situations. Every vessel is equipped with mechanical systems that need to operate accurately even as the vessel moves and is affected by the motion of the sea. So, what kind of dynamic analysis technologies should we use to analyze the behavior of these mechanical systems? The anchor is one of the essential systems on a vessel. When it is raised or lowered, its sharp parts must not damage the hull. This is made possible by the design that allows the anchor's orientation to change naturally as the chain moves through the guide. The system should be designed so that as the chain passes through the guide, contact naturally changes the anchor's orientation, thereby preventing the damages. To accurately simulate this motion, precise contact modeling and fast computation to handle the continuous chain movement efficiently are required. RecurDyn provides both the precise contact algorithms and exceptional computational speed for continuous systems like this. What you see here is a winch system commonly used on ships to wind ropes. As the rope interacts with the winch, you can see it slightly moving to one side and the behavior is produced through the dynamic simulation. To analyze this system, we need to consider how the rope, which is flexible, changes its shape as it winds around the drum, and also define accurate contact between the rope and the winch. In summary, when analyzing mechanical systems on ships, RecurDyn's capabilities in handling continuous systems, precise contact, and flexible body interactions become very important. For heavy cargo loaded onto ships, determining how to move and secure the cargo safely can be a significant challenge. To analyze this type of a problem, it is necessary to simulate not only the ship's motion on the water, but also the mechanisms that transport and secure the cargo. In cases where the cargo must be transported under high speed or high precision conditions, coupling with the control systems can be applied. This type of coupling with the control systems is also used in robotics and precision machinery. Therefore, analyzing such systems involves technologies including dynamic analysis, contact algorithms, flexible body analysis, and coupling with the control systems. As you can see, various types of floating structures can be installed at sea. Each of these structures involves a different kind of motion that needs to be analyzed. The dynamic behavior of mechanical systems placed on top, the motion of the mooring lines anchored to the seabed to keep the structure in position, and the interaction between the surrounding fluid and the entire system. In this example of a floating wind turbine, the effect of the wind on the blades is applied as a force that changes with wind speed and direction. This force is then used in the dynamic simulation to analyze how the turbine moves. To simulate this kind of a system accurately, both the motion of the floating body and the dynamic behavior of the mounted system need to be modeled using RecurDyn. A similar example can be found in offshore drilling rigs. These platforms can move due to ocean currents or waves, which may cause unexpected motion in the equipment and machinery installed on the deck. Such unexpected movement can even lead to serious accidents. To accurately model the cargo and equipment placed or secured on the deck, precise contact and force modeling along with advanced multibody dynamics are essential. In addition, the motion of the drilling rig itself, caused by currents or waves, can be analyzed using techniques such as 6DOF motion, buoyancy, and co-simulation with CFD, depending on the analysis objectives. Next, let's take a look at dynamic analysis related to shipbuilding operations on land. In shipyards, various types of equipment are used to transport heavy blocks. One of the most common examples is the Goliath crane here. These cranes lift and move extremely heavy blocks through the air. During these operations, unexpected accidents can occur due to the movement of this suspended load. By modeling and simulating these large structures and performing dynamic analysis in potentially dangerous real-world situations, we can better predict and prevent accidents before they occur. The simulation video in the center shows a dynamic model of a traditional Korean crane. In this model, pulleys and ropes were modeled using contact and force. The same modeling and analysis techniques can also be applied to modern cranes. The image in the lower right shows an example of a crawler crane simulation where contact forces and flexible bodies were used together with the tractor vehicle dynamics. This allows us to observe how the crane deforms and experiences stress as it moves while lifting a heavy block. When lifting or transporting a block, deformation can occur due to the loads applied to the points where the block is fixed. By defining the block itself as a flexible body in the dynamic model, we can analyze the result deformation and stress. We will continue to look at the dynamic analysis that can be applied in shipyards. In shipyards, heavy blocks are often placed and fixed on jigs or transported using multi-axle transporter vehicles. In such cases, the dynamic behavior of these heavy blocks can be analyzed and evaluated through dynamic simulation. Most of the related videos cannot be shared publicly, so I will explain using similar simulation result videos. To simulate a fixtured condition, contact and force algorithms must be accurate. With RecurDyn's contact and force capabilities, we can model a condition where the part is fixtured on the jig and the block is tied down to the support with traps or similar restraints. In the case of transporting a block with a multi-axle transporter, the block is placed on the vehicle and moved at a low speed. So, it is also important to model and analyze the multi-axle transporter that carries the block. Next, let's look at an example that simulates situations that may occur in a shipyard dock or canal. In these environments, it is necessary to analyze fluid flow within closed spaces or spaces that change over time. In addition, the motion of ships floating on the water also needs to be simulated. To accurately simulate such situations, we need not only to perform fluid analysis and multi-body dynamics simulations separately, but also to use coupled analysis so that the two simulations can interact and complement each other. So far, we have explored the applications of multi-body dynamics in the shipbuilding, offshore, and marine industries. In particular, we examined how to model and simulate the motion of floating structures and vessels, as well as RecurDyn's advanced dynamic analysis capabilities applicable to various systems. I hope RecurDyn will continue to be widely used across these industries, driving further innovation and development. That brings us to the end of today's session. I hope this webinar gives you useful insights and inspiration. If you'd like to learn more about what you covered today, or if you are interested in trying RecurDyn with a trial version, please feel free to contact us through the Function Bay website. Thank you so much for joining us today, and I look forward to seeing you soon again.